Hey guys, I'm back after a long hiatus, and today I'll be talking about remainder estimate for the integral test, something that you must have talked in your Calc 2 class while discussing sequence and series. So, this inequality is something I've seen a lot of people trip over, find confusing because the bounds for the integral are different in this case. Like there's n plus 1 over here, n over here, and people are often confused as to how this happened. So let me show you how we derive this. So to start off, let's define what the remainder is. Remainder, often denoted by Rn, is equal to S minus Sn, where S is the sum to infinity and Sn is the nth partial sum, or sum till the nth term, right? So S can be written as A1 plus A2 plus dot 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 plus An, the nth term, plus An plus 1 plus dot 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 again, plus goes on till infinity, right? You can just remove this. Yeah. And Sn, on the other hand, is the sum till nth term. So it is just A1 plus A2 plus dot 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 plus An. So if you look at this thing and this thing, then you get an idea that the remainder is simply an plus 1 plus an plus 2 plus dot 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 and so on. If you are to remove these items from this, then you are left with this, right? Yep, that's all I did. Nothing incredibly difficult. Let me erase this. Yep. And the remainder is also often known as the error. And why is that so? So it's because, let's say you have an extremely powerful computer and you calculate the series, calculate the sum of the numbers up until, let's say, 10,000th term. Okay? Let's say your computer is able to calculate the series up until the 10,000th term. What after that? Like, let's say your computer's limit is crossed there. Like you cannot go beyond the 10,000th term. You want to see if your sum up until infinity is closer to the partial sum that you found. If the difference between them is big or small, or you just want to find the relationship between them. So in this case, you can look at Sn, the nth partial sum, in this case up until the 10,000th term, to be the approximation, right? And this, the sum till infinity, to be the real sum. And the difference between the real sum and the approximation is the error. That's what we've learned throughout our math classes, physics classes, and whatnot, right? So the difference between the real sum and the approximation is the error, and in this case, it's the remainder. See the difference between S and Sn. So that's why it's also known as the error. So this is the introduction. Now let's see how we got this inequality that a lot of people dread. So for that, we have to take help of Riemann's sum. And let's see how that's done. So let's make a graph here. Let's say this is the fx, this is the curve fx, in which there are the points, the series. So what I'm trying to say is, let's say the series is 1 plus 2 plus 4 plus 8 plus so on. Then the 1, the 2, the 4, the 8, they are the points on the y-axis. So if you were to plot this series in a graph, then it would look something like this: 1 comma 1, 2 comma 2, 3 comma 4, and 4 comma 8. So these numbers are points on the y-axis. And for the x-axis, they are just the natural number starting from 1. So 1, 2, 3, 4, and goes on. So yeah, that's how you would graphically represent a series. So let's erase this. That was just some additional information for you. Yep. And since the remainder is concerned with an plus 1, an plus 2, and so on, let's say the points on the x-axis are n plus 1, n plus 2, n plus 3, and so on. Let me just do till n plus 3. So they are the points on the x-axis. So the points that correspond to them on the y-axis would be, I think, yeah, let me extend this, extrapolate. Okay, so let's say this is the point corresponding to, this is the point on the y-axis corresponding to n plus 1. So it would be f n plus 1. And this, if you were to extend it, then this would be f n plus 2. And this would be f n plus 3. I don't know if you've noticed or not, but the distance between n plus 1 and n plus 2 is just 1 unit. The distance between this is also 1 unit, because as I had shown you previously, if this were to be the series that we were concerned with, then this is how I'd graph it, right? 3 comma 4 and 4 comma 8. You see the points on the x-axis increase by only 1 unit. Therefore, the difference between them is 1 unit. So yeah, and let me connect this to here and this to here. You'll see in just a minute why I did so. Okay, so let's erase this as we don't need it anymore. Okay, so let's try and find the area of this rectangle. Okay, so the area is length into breadth. The breadth in this case is just 1 unit. See, it's just 1 unit over here, 1 unit over here. And the length in this case, which is this, is fn plus 2, right? This. And the f of n plus 2 is, what's that? It's an plus 1, an plus 2. What's that? It is an plus 2. So the area would be an plus 2 times 1 is an plus 2, right? So the area of this rectangle would be an plus 2. What about the area of this rectangle? It's the same process. It is an plus 3 times 1. The length, this length is an plus 3. Therefore, the area would be length times breadth. That would be an plus 3 times 1. That is an plus 3 itself. Now we've missed something. I've missed something over here. That is an plus 1. That seems to be missing. And that's not how I intended it to be, but it's missing, right? So what we can do is, let's just say this is f of n. Let's start with f of n. Let's start with n plus 1, n plus 2. So this way, this would be n plus 1. This would be n plus 1. this would be n plus 2. It's the same thing. I've not changed anything. It's still the same thing. Now, the only difference is the area of this now becomes an plus 1, and this becomes an plus 2. Why? Because the length, that is this, let me change the color to show, yeah, the length, that is this, is an plus 1. Why? Because this length is equal to this length, and see, this length is f of n plus 1, and f of n plus 1 is an plus 1. Therefore, the area for this rectangle would be an plus 1, and the area of this would be an plus 2. So now let's try to come up with an inequality. Obviously, you can see that the area enclosed by this graph, this curve, this one, is greater than the sum of the area enclosed by the rectangles, because as you can see, there's some extra patches over here like this and this. Therefore, what you can find out is area of the part enclosed by the curve, that is f of x, is greater than or equal to area, or let's say sum of area of the rectangles. Now this is in terms of words. Let's mathematically represent them. All right, so it would be f of x is greater than or equal to f of x dx, obviously is greater than or equal to an plus 1 plus an plus 2 plus dot 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 dot. Now I have not defined an upper bound and a lower bound. That's because I want to explain how we get the upper bound and the lower bound. So look at this. So since we are concerned about this rectangle as well, let's extrapolate this line, the line that I'm going on right now, this one. If you extrapolate it, go on and touch the curve, the graph, then you find it to be associated with n, right? F of n. So the upper bound is infinity. There is no doubt about that because we are going till infinity. But the lower bound here is n because we are concerned about the area from this point up until infinity. I hope you're clear on that. So the lower bound is n. And since this means the remainder, you can simply substitute it to be Rn, but let's just write the expanded version of it. Yeah. Okay, so we've found one inequality. Let's go for the other inequality. So this one was the right-hand point estimate. I hope you know what that is. And the other way would be using the left-hand estimate. So let's say this is the curve. F of x might not be identical, but I'm trying to use the same curve. And let's say this time this is n plus 1 and n plus 2. So let's extrapolate. Okay, I get that. Let's extrapolate this as well, right? Okay, let me extrapolate this as well, and let me. Yep. So I think we will be good with just two rectangles. So here you can see that the point on the rectangle, the left-hand point of the rectangle lies on the curve, and that's why it's known as the left-hand estimate. So if we were to find the area of this rectangle, then what would we have? the area we would have is the formula is the same, length times breadth. The breadth is 1 unit. We've already discussed why. The length would be f of n, right? Because see, the length is f of n, and f of n is an. So the area for this rectangle would be an. Now let's see what's the area for this rectangle. It would be the length is f of n plus 1 because as you can see it corresponds to n plus 1, so the area would be an plus 1, right? So as we know, the remainder starts from an plus 1 and not an is included in the nth partial sum, and remainder only starts from an plus 1th term. So this means that we're only concerned about the area from an plus 1, which means we're only concerned from this point onwards, from here. So we are not talking about this because that does not fall under the remainder, and we are only talking about remainder. So now if you see, the area enclosed by the curve f of x is less than the sum of area enclosed by the rectangles, because you can see, small triangles like this one also, are greater than the area enclosed by the curve. See, the area up until this point, let me change the color of the highlighter. It's the same, but it's these triangles that make the difference. Not exactly a triangle, but still, they're the ones who make the difference. Therefore, now we know that the area of the curve is less than or equal to an plus 1 plus an plus 2 and so on. Now what about the lower bound and the upper bound of the integral? What about it? Since we are starting from this line, this point, the lower bound is n plus 1 in this case and not n. So n plus 1, as we go up till infinity, it is infinity. Now let's combine inequality first and inequality second. What do we get? This is what we get. N plus 1, an plus 1 plus an plus 2. Oh, what was I doing? F of x Rn, because they are Rn, and f of x dx. I hope you got it. And the left hand estimate, this one, is often called as the overestimate. Why? Because the area of the rectangles is greater than the corresponding is greater than the area enclosed by the corresponding curve. And you must know that f of x is not just a random curve or a random graph that we have plotted. F of x is the curve that is concerned with the given series. That's the curve that we have derived from the given series. I'm sure you've talked about that in the integral test, so I'm not going to go over that. This is the overestimation because of these triangle looking things, and this is the underestimate because of these triangle looking stuffs, but now they make the area of the curve bigger than the area of the rectangles. So yeah, this is how we got the inequality. I hope you learned how to do this. It's been a long time since I made my last video, so maybe my explanations are a little rusty. If that's the case, then please let me know if you need any further explanation. Anyway, thank you for joining me on this one. I hope to see you in my next videos. Have a good day.